There are 400 billion stars in our galaxy alone. Many of them are billions of years older than our Sun. Even by the most conservative estimates, millions of planets in the Milky Way sit in habitable zones where liquid water could exist right now. The universe has had 13.8 billion years to produce life, intelligence, and civilizations capable of crossing the stars. The math says the galaxy should be teeming. Radio signals should flood every frequency. Probes should have visited every star system, including ours, millions of years ago. But when we point our telescopes outward and listen, we hear nothing. Absolute silence. In 1950, the physicist Enrico Fermi asked the question that still haunts science today. Where is everybody? The answer might be the most terrifying idea humanity has ever confronted. If you enjoy deep explorations into the biggest questions science has ever asked, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow and lets me keep making these journeys for you. Get comfortable. We're about to explore the darkest possibility the universe offers. Together, let's begin. It was an ordinary summer lunch in 1950. The sun beat down on the desert mesas of Los Alamos, New Mexico. A group of physicists walked toward the cafeteria at the laboratory where, just 5 years earlier, they had helped build the most destructive weapon in human history. The conversation was light. Someone had brought up a recent New Yorker cartoon depicting aliens stealing municipal trash cans from New York City streets. The physicists laughed. The topic drifted to flying saucer reports that had been filling newspapers that year. They joked about the sightings, traded theories, and moved on to other things. Then, in the middle of lunch, with no particular build-up or dramatic pause, the physicist Enrico Fermi set down his fork and asked a question that would haunt science for the next 75 years. Where is everybody? His colleagues laughed at first because the question sounded casual, almost like a punchline, but Fermi was not joking. He had been running numbers in his head during the walk to the cafeteria. He was one of the greatest intuitive calculators who ever lived, a man who could estimate the yield of a nuclear explosion by dropping scraps of paper into the blast wave, and the numbers he was running told him something profoundly strange. Given the age of the galaxy, the number of stars it contained, and the likelihood of planets forming around those stars, intelligent civilizations should have had more than enough time to arise, develop technology, and spread across the Milky Way. Not once, not twice, thousands of times. The galaxy should be saturated with evidence of intelligence. Signals should be everywhere. Probes should have reached every corner of every star system. Yet when humanity looked outward, it found nothing. No signals, no probes, no structures, no evidence of any kind that anyone else had ever existed. Fermi did not publish a formal paper on this question. He did not write it up or present it at a conference. He simply asked it at lunch. But the physicists at that table understood immediately that the question carried weight far beyond its casual delivery. Edward Teller, who was present, later recalled that Fermi made a series of rapid calculations and concluded there was a fundamental contradiction between the high probability of extraterrestrial civilizations and the total absence of evidence for them. The probability said they should be here. Reality said they were not. Something in our assumptions had to be wrong. That contradiction became known as the Fermi Paradox, and it remains one of the most disturbing unsolved problems in science. Not because it is technically complex, the math is relatively straightforward, but because every attempt to resolve it leads to conclusions that are either deeply strange or deeply unsettling. To understand why, you need to see the numbers Fermi was working with, and those numbers start with the galaxy itself. The Milky Way is enormous beyond any scale the human mind evolved to process. It contains approximately 400 billion stars, not million, billion. If you started counting those stars at a rate of 1 per second, it would take you more than 12,000 years to finish. You would have started counting before the invention of agriculture, and you would still not be done today. Those 400 billion stars are spread across a disk, roughly 100,000 light-years in diameter, spinning slowly around a common center of gravity. Our Sun sits about 26,000 light-years from the galactic core, embedded in one of the galaxy's spiral arms, orbiting the center once every 230 million years. But here is the detail that makes the Fermi Paradox bite. Our Sun is not particularly old. It formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust. That sounds ancient by human standards, but on galactic timescales it makes our solar system a relative newcomer. The Milky Way itself began forming roughly 13.6 billion years ago. The oldest stars in our galaxy have been burning for more than 13 billion years. This means billions of stars in our galaxy had a head start of 5, 6, 7, even 8 billion years over our Sun. Whatever happened on Earth, the process of stellar evolution, planet formation, and potentially biological development could have begun around other stars billions of years before our solar system even existed. Let that sink in. Billions of years is not a rounding error. It is an almost incomprehensible stretch of time. Life on Earth went from single-celled organisms to a species capable of splitting atoms and landing on the Moon in roughly 4 billion years. A civilization that got started around an older star, even one that evolved at the same sluggish pace as life on Earth, could have reached technological maturity billions of years before the first microbe appeared in Earth's oceans. And stars capable of hosting habitable planets are not rare, they are shockingly common. NASA's Kepler Space Telescope, which operated from 2009 to 2018, surveyed more than 150,000 stars and discovered that planets are everywhere. Not just gas giants orbiting close to their parent stars, but rocky Earth-sized worlds sitting in the habitable zone, the orbital region where temperatures allow liquid water to exist on a planet's surface. The data from Kepler, confirmed and expanded by subsequent missions, suggests that roughly 1 in 5 Sun-like stars hosts at least one rocky planet in the habitable zone. Apply that ratio to the Milky Way's population of Sun-like stars, and you get approximately 11 billion potentially habitable Earth-sized worlds in our galaxy alone. Expand the count to include planets around red dwarf stars, which are far more numerous than Sun-like stars, and the number climbs to tens of billions. Tens of billions of potentially habitable worlds, in a galaxy that has been producing them for over 13 billion years, and the raw materials for life are not confined to Earth. Astronomers have detected complex organic molecules in interstellar gas clouds, in the tails of comets, in meteorites that fall to Earth's surface. Amino acids, the building blocks of proteins, form naturally in space. Water is one of the most common molecules in the universe, found on moons, asteroids, and in the frozen outer regions of countless star systems. The chemical ingredients necessary for biology are not rare or special. They are scattered across the galaxy like seeds blown across a field. This is the foundation of the paradox. The galaxy is old, habitable planets are abundant, the chemistry of life is commonplace. The time available for evolution is immense. Every factor we can measure suggests the Milky Way should have produced intelligent civilizations long before our Sun was born. And yet, we see nothing. In 1961, 11 years after Fermi's lunch, the astronomer Frank Drake attempted to formalize this problem. Drake was organizing the first scientific conference on the search for extraterrestrial intelligence, held at the Green Bank Observatory in West Virginia. He needed a way to structure the discussion, so he wrote an equation on the blackboard. It was not meant to produce a single definitive answer. It was meant to organize the question, to break the problem of extraterrestrial intelligence into individual factors that could be discussed, estimated, and debated one at a time. The Drake equation multiplies 7 variables together to estimate the number of communicative civilizations currently existing in the Milky Way. Each variable represents one step in the chain, from raw stellar material to a civilization capable of sending detectable signals. The first variable is the rate of star formation in the galaxy. Astronomers have measured this with reasonable confidence. The Milky Way produces approximately 1.5 to 3 new stars per year, This is a well-constrained number. The second variable is the fraction of those stars that form planetary systems. Thanks to Kepler and subsequent missions, we now know this fraction is high. Most stars have planets. Current estimates suggest the fraction is close to 1, meaning nearly every star has at least one planet. The third variable is the average number of planets per star system that could potentially support life. This includes rocky planets in the habitable zone, but also moons with subsurface oceans, like Jupiter's moon Europa. Conservative estimates place this between 1 and 5 per system that has habitable zone candidates. The fourth variable is the fraction of those suitable planets where life actually appears. This is where certainty begins to collapse. We have exactly one data point: Earth. Life appeared on Earth relatively quickly after conditions stabilized, within a few 100 million years of the planet's formation. Some scientists interpret this as evidence that life arises easily whenever conditions permit. Others argue that a sample size of 1 tells us almost nothing, and that life's origin might be a fantastically rare event. The honest answer is that nobody knows. The fifth variable is the fraction of life-bearing planets where that life evolves intelligence. Again, we have one example. Life existed on Earth for approximately 3.5 billion years before anything resembling human-level intelligence appeared. Hundreds of millions of distinct species have existed on this planet. Only one developed technology. Intelligence is clearly not an inevitable outcome of evolution. It is one strategy among many, and most successful organisms never develop it. The sixth variable is the fraction of intelligent species that develop technology capable of producing detectable signals, things like radio transmissions, laser pulses, or large-scale engineering projects. Even on Earth, anatomically modern humans existed for roughly 200,000 years before inventing radio technology. The window between biological intelligence and technological civilization is not automatic. The seventh variable is the most important and the most terrifying. It is the average length of time that a communicative civilization survives. This variable, usually denoted as L in the equation, determines everything. A civilization that broadcasts signals for 10 million years fills the galaxy with its presence. A civilization that broadcasts for 200 years is a momentary flicker, so brief that the odds of anyone else being around to hear it become vanishingly small. When Drake first presented his equation, participants at the Green Bank Conference plugged in optimistic values and estimated that the galaxy might contain anywhere from 1,000 to 100 million communicative civilizations. The mood was hopeful, the universe seemed crowded. But those early estimates depended heavily on optimism about the final variable, the lifespan of civilizations. If you assume civilizations endure for millions of years, the galaxy fills up quickly. If you assume they last only a few centuries, the galaxy empties out just as fast. The Drake equation does not solve the Fermi Paradox. It sharpens it. It shows precisely where the uncertainties hide and forces you to confront the questions we are least equipped to answer. And the hardest question is not about stars or planets or chemistry. It is about survival. Set aside the Drake equation for a moment and consider the paradox from a purely logistical perspective. Forget about signals and communication. Think about physical expansion. Think about what happens when a civilization decides to spread. In 1980, the physicist Frank Tipler published a thought experiment that made the Fermi Paradox even more disturbing. Tipler argued that a civilization does not need faster-than-light travel or any exotic technology to colonize the galaxy. It only needs self-replicating probes. Imagine a civilization that builds a single robotic spacecraft capable of traveling to a nearby star system at even a modest fraction of the speed of light, say 10%. At that speed, the probe reaches the nearest star in roughly 40 years. Upon arrival, the probe uses local resources, asteroids, comets, dust, to build copies of itself. Those copies launch toward additional star systems. Each new arrival builds more copies. The process repeats. This is exponential growth applied to interstellar distances, and the math is striking. Even accounting for travel times between stars and construction delays at each stop, a single wave of self-replicating probes could visit every star system in the Milky Way in approximately 1 million to 10 million years. That sounds like a long time by human standards. On a galactic timescale, it is an eye blink. The galaxy has existed for more than 13 billion years. 1 million years represents less than 1/100th of 1% of that history. This means that if even one civilization anywhere in the Milky Way, at any point in the galaxy's 13 billion year history, had developed self-replicating probes and launched them, those probes would have reached every star in the galaxy by now, including ours. The fact that we observe no such probes, no alien artifacts in our solar system, no evidence of past visitation, no megastructures around other stars, constitutes a data point so striking that it cannot be casually dismissed. And it gets worse. The argument does not require self-replicating probes. It does not even require deliberate colonization, a civilization that simply expanded outward at a slow, steady pace, settling nearby star systems the way Polynesian navigators island hopped across the Pacific, would still fill the galaxy in a few million years. The key insight is not about speed or technology. It is about time. The galaxy is so old that even the slowest conceivable expansion would have saturated it many times over. The universe has been running this experiment for billions of years. The expected result is a galaxy teeming with evidence of intelligence. The observed result is total silence. Scientists have now been searching for that evidence for more than 60 years. The search for extraterrestrial intelligence, or SETI, began in 1960, when Frank Drake pointed a radio telescope at two nearby stars and listened for signals. He heard nothing. Since then, SETI programs have surveyed millions of stars across a wide range of radio and optical frequencies. The Allen Telescope Array, the Breakthrough Listen Initiative, and dozens of other projects have scanned the skies with instruments far more sensitive than anything Drake had access to. The result is always the same: silence. No artificial radio signals, no laser pulses, no repeating patterns that suggest intelligence. The search has not covered every star or every frequency, and SETI researchers are quick to point out that absence of evidence is not evidence of absence. But the sheer scale of the search, combined with the mathematical expectation that the galaxy should be filled with signals, makes the silence increasingly difficult to explain. Astronomers have also searched for indirect evidence of advanced civilizations. If a species built a Dyson sphere, a hypothetical megastructure that surrounds a star to capture its entire energy output, it would radiate waste heat detectable as an infrared signature. In 2015, scientists surveyed approximately 100,000 galaxies, looking for excess infrared radiation consistent with galaxy-spanning civilizations, harvesting stellar energy. They found nothing anomalous. A separate survey examined 250,000 individual stars in the Milky Way for infrared signatures suggesting partial Dyson structures. Again, nothing. The Gaia spacecraft, which has mapped the positions and motions of nearly 2 billion stars in our galaxy, provides another window. If civilizations had constructed large artificial structures or significantly modified their stellar environments, those alterations might show up as anomalies in stellar data. So far, no such anomalies have been identified. Even our own solar system has been examined. If self-replicating probes had visited our star system at any point in the past several billion years, they might have left artifacts on the Moon, on asteroids, or in stable orbital positions called Lagrange points. Searches of these regions have found nothing artificial. The Moon's surface preserves a record stretching back billions of years, essentially a fossil record of everything that has passed through our neighbourhood. That record shows no sign of visitation. The silence is not limited to our immediate surroundings. It extends as far as our instruments can reach, and with each passing year, with each new telescope and each expanded survey, the silence only deepens. The history of that search stretches back to the very beginning of modern radio astronomy. In 1960, Frank Drake conducted Project Ozma, humanity's first deliberate attempt to detect extraterrestrial signals. He pointed the 85-foot Tatel telescope at Green Bank, West Virginia, toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened at a single frequency near the hydrogen emission line of 1420 MHz. He listened for approximately 150 hours over the course of 4 months. The result was silence. In the decades that followed, SETI programs grew dramatically in scope and sensitivity. The Ohio State University Big Ear Telescope scanned the sky continuously throughout the 1970s. On August 15, 1977, the telescope recorded a narrowband radio signal so strong and so unusual that astronomer Jerry Eman circled the data printout and wrote, "Wow," in the margin. The signal lasted 72 seconds. It came from the direction of the constellation Sagittarius. It bore many of the hallmarks of an artificial transmission: narrowband, strong, and at a frequency near the hydrogen line where scientists had long predicted intelligent beings might broadcast. For a brief moment it looked like contact, but the wow signal was never detected again. Eman and other astronomers pointed telescopes at the same patch of sky hundreds of times over the following years and decades. Nothing. The signal never repeated. Without repetition, scientists could not confirm its origin, could not rule out terrestrial interference or an unusual natural phenomenon, and could not declare it evidence of intelligence. It remains the most tantalizing detection in SETI history, and simultaneously one of its greatest frustrations. A single burst that might have been everything or might have been nothing, and no way to tell the difference. NASA launched its own SETI program in 1992, a systematic survey called the High Resolution Microwave Survey, designed to scan millions of frequencies across the entire sky. Congress killed the funding after just 1 year. The program was ridiculed by some legislators as a waste of taxpayer money, a search for little green men. Private donors eventually stepped in, and the project was reborn as Project Phoenix under the SETI Institute, surveying approximately 800 nearby star systems over nearly a decade. It found nothing. The most ambitious modern effort is Breakthrough Listen, launched in 2015 with $100 million in funding from the billionaire Yuri Milner. Breakthrough Listen uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to survey the 1 million stars closest to Earth, the entire galactic plane, and the 100 nearest galaxies. It covers a frequency range from 1 to 12 GHz and processes data at a rate that dwarfs all previous SETI programs combined. As of the mid-2020s, Breakthrough Listen has surveyed millions of star systems. The result, once again, is silence. In 2020, a team of Australian astronomers published the results of the most comprehensive SETI survey of its kind at that time. Using the Murchison Wide Field Array radio telescope, they observed over 10 million stellar sources in the southern sky. They searched for narrowband signals that might indicate artificial transmission. They found nothing. 10 million stars, 0 detections. Each generation of instruments is more sensitive. Each survey covers more sky, more frequencies, more star systems. And each time, the answer is the same. This is what makes the Fermi Paradox more than an abstract puzzle. It is not a thought experiment that can be resolved by clever argument or dismissed with a shrug. It is an empirical observation backed by decades of data. The galaxy is old enough, large enough, and chemically rich enough that intelligent civilizations should have arisen many times over. The time required for even slow interstellar expansion is a tiny fraction of the galaxy's age. Our instruments are now sensitive enough to detect numerous forms of evidence that advanced civilizations might leave behind. And when we look, we find nothing. Something about our assumptions must be wrong. Either intelligent life is far rarer than the numbers suggest, or something prevents civilizations from reaching the point where they become visible, or something we have not yet imagined is filtering intelligence out of the cosmic equation? The possible answers to Fermi's question are not all equal. Some are hopeful. If life itself is extraordinarily rare, then the silence means we are special, a cosmic anomaly in an empty galaxy. That would make our existence precious beyond measure. But other answers are far less reassuring. If life is common and intelligence is achievable, then the silence implies something darker, that civilizations routinely fail, that they hit barriers they cannot overcome, that intelligence itself carries the seeds of its own destruction. The astrophysicist Michael Hart formalized this tension in 1975 when he argued that the absence of extraterrestrial visitors to Earth requires one of four explanations. Either interstellar travel is physically impossible, which contradicts what we know about physics, or intelligent species uniformly choose not to explore, which requires an implausible level of universal agreement. Or they have not had enough time to reach us, which contradicts the age of the galaxy, or they do not exist. Hart considered the last option the most likely. His conclusion was stark. We are alone. Not because the universe is hostile, but because intelligence may simply never arise more than once in a galaxy. But there are possibilities Hart did not fully consider. Possibilities that are in some ways more frightening than simple loneliness. What if civilizations do arise? What if they arise frequently, but something systematically prevents them from surviving long enough to be noticed? What if the galaxy is not empty but littered with the corpses of civilizations that flared briefly and then went dark? The possible explanations for the Fermi Paradox fall into broad categories, and each category reveals something uncomfortable about the universe we inhabit. Some explanations challenge our understanding of biology. Others challenge our assumptions about technology. Still others challenge our confidence in the long-term survival of intelligent species. The silence has explanations, but each one carries implications that grow more unsettling the deeper you examine them. And the deepest explanation, the one that keeps researchers awake at night, is the possibility that there is something about the nature of civilizations themselves, something built into the structure of intelligence and technology that makes long-term survival nearly impossible. To see why, we need to dismantle the easy answers first and confront the ones that remain. The first objection everyone raises is distance. Space is unimaginably vast. Stars are separated by light years of empty vacuum. Radio signals weaken with the square of the distance, fading into background noise long before they cross the galaxy. Even travelling at the speed of light, the absolute fastest anything can move through the universe, a message from one side of the Milky Way to the other would take 100,000 years to arrive. Maybe the silence is not mysterious at all. Maybe the galaxy is simply too big for anyone to reach anyone else. This sounds reasonable, it feels intuitive, and it is almost certainly wrong as a complete explanation. The distance argument fails because it treats the problem as if civilizations exist only right now, as if the question is whether two civilizations alive at this exact moment could find each other across the stellar void. But that is not what the Fermi Paradox asks. The paradox asks why, across the entire 13.6 billion year history of the galaxy, with billions of stars forming billions of years before our sun, no civilization has ever managed to leave a detectable trace. Distance is a barrier to conversation, but it is not a barrier to expansion over deep time. As we have already seen, even slow expansion at a fraction of light speed, using technology not dramatically beyond what humanity can already envision, would fill the galaxy in 1 to 10 million years. The galaxy has had enough time for that process to complete more than 1,000 times over. Light speed limits make real-time communication impractical. They do not make colonization, exploration, or the construction of detectable megastructures impossible. The mechanical explanation, that space is simply too big, addresses a real constraint. But it does not resolve the paradox. It just makes the silence slightly less surprising for any single moment. Stretch the timescale to billions of years, and the silence becomes deafening again. So if distance alone cannot explain the emptiness, what can? Scientists, philosophers, and researchers have proposed dozens of solutions over the decades since Fermi asked his question. Each one attempts to reconcile the high probability of extraterrestrial intelligence with the total absence of evidence. Each one carries assumptions, and each one, when examined carefully, reveals limitations that prevent it from providing a fully satisfying answer. To understand why the paradox remains unresolved, you need to see how these explanations work and why each one falls short. The first major category is what scientists call the zoo hypothesis. Proposed by the astronomer John Ball in 1973, this idea suggests that advanced extraterrestrial civilizations already know about us. They have detected Earth. They may even be observing us right now. But they have made a deliberate choice not to interfere, not to reveal themselves, not to make contact. We are like animals in a wildlife preserve, studied from a distance by beings who have decided that non-intervention is the ethical or strategic choice. This idea has a certain elegance. It resolves the paradox without requiring that intelligent life is rare. It allows the galaxy to be teeming with civilizations while explaining why we detect nothing. It mirrors something humans themselves do. We establish national parks where we observe wildlife without contact. We have ethical debates about interfering with uncontacted tribes in the Amazon. The idea that a vastly more advanced civilization might apply similar principles to a species like ours does not seem unreasonable. But the zoo hypothesis has a fatal weakness, and it lies in the problem of coordination. For the zoo to work, every civilization in the galaxy must independently arrive at the same decision. Not just one. Not just most. Every single one. Across billions of years and potentially thousands or millions of independently evolved intelligences, not one species, not one faction within a species, not one rogue individual with access to a transmitter has ever broken the quarantine. Not once in the entire history of the galaxy. Think about what that requires. Human civilization cannot even achieve consensus among nations on a single planet. We cannot agree on climate policy, trade regulations, or nuclear weapons treaties. The idea that thousands of alien civilizations scattered across a galaxy, separated by vast distances and operating under completely independent evolutionary histories, would all unanimously agree on a single behavioral policy, strains credibility to its breaking point. One defector is all it would take. One civilization that decides to transmit. One individual who aims an antenna at a promising star. One probe that enters our solar system by accident. Across billions of years, the probability of perfect universal compliance approaches zero. The zoo hypothesis is not impossible, but as a universal explanation for the silence, it requires a level of coordination that seems far less probable than the alternatives it is trying to avoid. There is a darker variation on the idea of deliberate silence, one rooted not in benevolence but in fear. It is sometimes called the dark forest hypothesis, drawn from a concept explored by the Chinese science fiction author Liu Cixin, but grounded in real principles of game theory and evolutionary logic. The argument proceeds as follows. Imagine a galaxy containing multiple civilizations, each aware that others might exist but unable to determine their intentions. The distances between stars make verification impossible. You cannot visit a neighboring civilization to assess whether it is friendly or hostile. You cannot send a diplomatic envoy and wait for a response when the round trip might take centuries. All you know is that another intelligence exists, that it has access to technology you may not fully understand, and that its survival interests may conflict with your own. In this scenario, game theory suggests a chilling optimal strategy. Any civilization that reveals its location risks annihilation by a more powerful or more paranoid neighbor. The safest course of action is to remain silent. And if you detect another civilization broadcasting its position, the safest response, from a purely strategic standpoint, is to destroy it before it can develop the capacity to threaten you. Not because you are evil, not because you want conflict, but because you cannot afford to gamble your species' survival on the assumption that a stranger across the galaxy shares your values. Under dark forest logic, the galaxy becomes a silent wilderness where every civilization hides, listens, and fears. Broadcasting your existence is not a hopeful act of outreach. It is a death sentence. The silence we observe is not the absence of civilizations. It is the sound of civilizations that have learned, perhaps through bitter experience, that being heard means being targeted. This hypothesis has an emotional power that few other explanations can match. It transforms the Fermi Paradox from a question about absence into a question about predation. The cosmos becomes not empty but hostile, a landscape where silence is the only survival strategy. But the dark forest hypothesis faces its own serious problems. First, it assumes that interstellar destruction is both possible and practical. Destroying a civilization across interstellar distances would require technology of almost unimaginable scale and precision. Aiming a relativistic projectile or a directed energy weapon at a star system dozens of light years away, with enough accuracy to ensure destruction, pushes the boundaries of what physics allows, even in theory. Second, the hypothesis requires that every civilization independently arrives at the same paranoid conclusion. Just as the zoo hypothesis requires universal cooperation, the dark forest requires universal distrust. One civilization that broadcasts openly, even recklessly, would break the pattern. Across billions of years and potentially thousands of independent species, the emergence of at least one open broadcaster seems probable. Third, there is no evidence of interstellar violence anywhere in the galaxy. No disrupted star systems, no sterilized planets, no signs of weapons discharge at cosmic scales. If civilizations were routinely destroying each other, the aftermath should be detectable. We see nothing of the sort. The dark forest remains a compelling thought experiment and a powerful piece of speculative fiction. As a complete scientific explanation for the Fermi paradox, it requires assumptions that the evidence does not currently support. The second major explanation is the rare earth hypothesis, and it takes the paradox in a completely different direction. Instead of arguing that civilizations exist but hide, it argues that the conditions necessary for complex life are so extraordinarily specific that Earth may be one of vanishingly few places in the galaxy where they all came together. This idea was formalized by the geologist Peter Ward and the astronomer Donald Brownlee in their 2000 book, and it remains one of the most scientifically grounded responses to the Fermi paradox. The argument is not that habitable planets are rare. We know from Kepler data that rocky planets in habitable zones are common. The argument is that being in a habitable zone is just the beginning of a much longer list of requirements, and each additional requirement makes the odds worse. Start with the star itself. Not all stars are equally hospitable. Red dwarfs, which make up roughly 70% of all stars in the galaxy, are problematic hosts for life. They are prone to violent stellar flares that can strip a planet's atmosphere. Many red dwarf habitable zone planets are tidally locked, presenting one face permanently to their star, creating extreme temperature differences between the light and dark sides. Stars that are too massive burn through their fuel too quickly, dying in supernova explosions before complex life has time to evolve. The window of stellar types that provide stable, long-lived energy for billions of years is narrower than it first appears. Then consider the planet itself. Earth has a powerful magnetic field generated by its molten iron core. This magnetic field creates a magnetosphere that deflects charged particles from the solar wind. Without it, the solar wind would gradually strip away our atmosphere, as it did to Mars. Mars once had a thicker atmosphere and liquid water on its surface. When its core cooled and its magnetic field collapsed, the solar wind eroded its atmosphere over millions of years, leaving the cold, barren world we observe today. A habitable zone planet without a strong magnetic field may be a dead planet waiting to happen. Earth also has plate tectonics, a geological process where the planet's crust is broken into moving plates that recycle material between the surface and the interior. This process regulates carbon dioxide levels in the atmosphere over geological timescales through the carbon silicate cycle. Without plate tectonics, carbon dioxide would accumulate unchecked. leading to a runaway greenhouse effect like the one that turned Venus into a furnace with surface temperatures of 460 degrees Celsius. Or carbon dioxide would deplete entirely, leading to a frozen world. Plate tectonics acts as a planetary thermostat, and not all rocky planets have it. The mechanism appears to require a specific combination of planetary size, composition, and internal heat that may not be universal. Then there is the Moon. Earth's moon is unusually large relative to its parent planet, approximately 1/4 of Earth's diameter. This oversized companion stabilizes Earth's axial tilt, preventing wild oscillations that would cause extreme climate swings over millions of years. Mars, which lacks a large stabilizing moon, has experienced axial tilts ranging from approximately 15 to 45 degrees over geological time, producing chaotic climate variations. A stable axial tilt may be essential for complex life to evolve over billions of years. The formation of Earth's moon is believed to have resulted from a giant impact between the early Earth and a Mars-sized body approximately 4.5 billion years ago. That collision was a specific event, not a guaranteed outcome of planetary formation. Many habitable zone planets may never experience such an impact. Many that do may be destroyed by it rather than gaining a stabilizing companion. Jupiter plays a role as well. Our solar system's largest planet, sitting in the outer regions, acts as a gravitational shield. Its immense gravity deflects or captures many of the comets and asteroids that would otherwise bombard the inner planets. Without Jupiter, the impact rate on Earth would be significantly higher, potentially sterilizing the surface frequently enough to prevent complex life from gaining a foothold. Computer models suggest that solar systems without a Jupiter-like guardian may experience impact rates several times higher than ours. Not every star system comes equipped with a conveniently placed gas giant. The rare Earth hypothesis stacks these requirements on top of each other. The right type of star, a rocky planet in the habitable zone, a strong magnetic field, active plate tectonics, a large stabilizing moon formed by a specific type of giant impact, a gas giant in the outer system to reduce bombardment rates, the right distance from the galactic center to avoid excessive radiation from nearby supernova and gamma ray bursts, while still having access to enough heavy elements for rocky planet formation. This last requirement deserves particular attention because it constrains where complex life can arise within the galaxy itself. Astronomers call it the galactic habitable zone, a concept analogous to the stellar habitable zone around individual stars but applied to the entire Milky Way. The galactic habitable zone is the region of the galaxy where conditions are favorable for the development of complex life. Move too close to the galactic center, where stars are densely packed and supernova explosions occur frequently, and the radiation environment becomes lethal. A planet orbiting a star in the inner galaxy might be bathed in gamma radiation from a nearby supernova every few million years, each event potentially stripping away atmospheric ozone and exposing the surface to sterilizing ultraviolet light. Complex surface life would be repeatedly set back to zero, never gaining enough uninterrupted time to evolve beyond simple microbial forms. Move too far from the galactic center, and a different problem emerges. The outer regions of the galaxy are metal poor. Stars in these regions formed from gas clouds that had not been enriched by many previous generations of stellar nucleosynthesis. Fewer heavy elements means fewer rocky planets. Carbon, oxygen, silicon, iron, the materials that build terrestrial worlds and the complex chemistry of life, are less abundant in the galactic outskirts. A star system in the far outer disk might have gas giants but lack the raw ingredients for an Earth-like world. The sweet spot lies in between. Current models estimate the galactic habitable zone occupies a ring extending from roughly 13,000 to 33,000 light-years from the galactic center. Our solar system sits at approximately 26,000 light-years, comfortably within this band, but the habitable zone contains only a fraction of the galaxy's total stellar population. Stars inside it represent perhaps 20 to 30% of the Milky Way's 400 billion stars. The pool of candidates for complex life is immediately reduced by more than 2/3 before any other factors are considered. Furthermore, the galactic habitable zone has shifted over cosmic time. In the early galaxy, heavy elements were scarce everywhere. The zone was narrow or possibly non-existent. As successive generations of stars produced and distributed heavy elements, the zone gradually expanded outward. Stars that exist in the habitable zone today may not have been in favourable positions when they first formed billions of years ago. The temporal dimension of the galactic habitable zone further constrains the number of star systems that have been suitable for complex life for long enough to produce it. Each factor individually might be moderately common, but the probability of all of them occurring simultaneously around the same star drops dramatically with each additional requirement. This argument is scientifically compelling. It does not require any exotic physics or speculative sociology. It uses known astrophysical and geological processes to argue that complex life requires a very specific set of conditions that most planets will never satisfy, and it provides a credible explanation for why Earth-like worlds with thriving biospheres might be extraordinarily rare. But the rare Earth hypothesis has its own limitation. It explains rarity, not total silence. Even if only 1 in a billion star systems produces complex life, the Milky Way contains 400 billion stars. That still yields hundreds of civilizations in our galaxy alone. Scale the argument to the observable universe, which contains approximately 2 trillion galaxies, and even the most aggressive version of the rare Earth hypothesis still predicts enormous numbers of civilizations across cosmic space. The hypothesis makes the paradox less severe, but it does not eliminate it entirely. It pushes the expected number of civilizations down, but unless the probability of each required condition is almost infinitely small, it cannot push that number to 0. The third major explanation involves a mismatch in communication technology. Perhaps civilizations exist throughout the galaxy, broadcasting their presence vigorously, but they use methods we cannot detect. Humanity has been searching primarily for radio signals, and more recently, for optical laser pulses. These are the technologies we understand, but a civilization even a few centuries more advanced than ours might communicate using methods we have not yet discovered or cannot currently detect. Gravitational wave communication is one theoretical possibility. Gravitational waves, ripples in space-time predicted by Einstein and first directly detected in 2015, propagate at the speed of light and can pass through matter without being absorbed. A sufficiently advanced civilization might modulate gravitational waves to carry information, creating a communication channel that our current detectors, designed to observe natural astrophysical events, would not recognize as artificial. Neutrino communication is another option. Neutrinos are subatomic particles that interact with matter so weakly that they pass through entire planets without stopping. A civilization that could generate and modulate beams of neutrinos would possess a communication channel almost impossible to intercept or block. Our neutrino detectors are extraordinarily crude compared to what would be needed to decode an artificial neutrino signal. There are even more speculative possibilities. Quantum communication protocols that exploit entanglement. Transmission methods based on physics we have not yet discovered. Communication through modifications to stellar output or gravitational lensing that we would not recognize as artificial. The universe may be humming with alien conversation on channels we lack the instruments to tune into. This explanation is honest about the limits of human technology. We have been listening for a cosmically insignificant period of time, using instruments designed to detect a narrow range of signal types. Concluding that the galaxy is silent based on 60 years of searching with primitive equipment is like scooping a glass of water from the ocean, finding no fish in it, and concluding the ocean is empty. The analogy, often attributed to SETI researcher Jill Tarter, highlights how small our search has been relative to the vastness of the problem. But the communication mismatch argument suffers from the same coordination problem as the zoo hypothesis. For this to fully explain the silence, every civilization in the galaxy must have independently abandoned electromagnetic communication. Not one species, not one faction, not one hobbyist with a radio transmitter continues to broadcast on frequencies we can detect. Across billions of years, no one anywhere uses radio. This seems unlikely. Even if advanced civilizations move to exotic communication methods, the transition period during which they use radio, potentially lasting centuries or millennia, should leave detectable traces. A galaxy full of civilizations at various stages of development should include some that are still in their radio phase. Just as our galaxy contains stars at every stage of stellar evolution, the absence of even primitive signals from civilizations in transition demands an explanation that communication mismatch alone cannot provide. The fourth explanation is perhaps the most creative and the most psychologically interesting. It suggests that advanced civilizations do not expand outward because they turn inward instead. This idea proposes that any sufficiently advanced species will eventually develop virtual realities, simulated environments, or digital forms of existence so compelling that physical exploration of the cosmos loses all appeal. Why cross the void between stars when you can build infinite worlds inside a computer? The concept has gained traction as human technology has moved in precisely this direction. Virtual environments are becoming more immersive. Artificial intelligence grows more capable each year. Some researchers in neuroscience and philosophy have argued that consciousness itself might be substrate independent, meaning it could run on silicon or quantum processors just as easily as on biological neurons. If a civilization can upload its minds into digital form, it gains access to experiences that the physical universe cannot provide. Customized realities running at accelerated clock speeds. Improvit, simulated universes where the laws of physics can be rewritten. Environments where suffering, scarcity, and death are eliminated. A civilization that makes this transition might withdraw from the physical galaxy entirely. It would have no reason to build megastructures, send probes, or broadcast signals. Its entire existence would be contained within computing hardware that, from an astronomical perspective, might be indistinguishable from a small warm object orbiting a star. We could be surrounded by billions of digital civilizations and never know, because their infrastructure leaves no signature we would recognize as artificial. This is a genuinely fascinating possibility. It takes the Fermi Paradox and reframes it not as a question about survival or rarity, but as a question about motivation. Maybe intelligence does not inevitably lead to expansion. Maybe it leads to introspection. Maybe the natural endpoint of technological development is not a galaxy-spanning empire, but a quiet server running in the dark. But like the zoo hypothesis and the communication mismatch argument, the inward turn explanation requires universality. Every civilization must independently make this choice. Not one species across the entire history of the galaxy must choose to remain physically active, to explore, to expand, to build visible structures in the cosmos. Even if 99% of civilizations turn inward, the remaining 1% should have filled the galaxy many times over. Expansionist civilizations, by definition, are the ones that leave evidence. They are the ones that would be visible. The fact that we see nothing means either expansionist civilizations do not exist or they do not survive long enough to make their presence known. Each of these explanations captures something plausible about the universe. The zoo hypothesis addresses the possibility of deliberate concealment. The rare Earth hypothesis addresses the possibility that complex life is unusual. The communication mismatch addresses the limits of our detection technology. The inward turn addresses the possibility that expansion is not a universal drive. Each one could be partially true. Some combination of these factors might reduce the number of detectable civilizations in the galaxy, but none of them, individually or in combination, fully resolves the paradox as long as the expected number of civilizations remains even moderately high. And that is the crux of the problem. The numbers are so large, the timescales so vast, and the galaxy so old that partial explanations are not enough. Even if complex life is rare, even if most civilizations hide, even if communication methods diverge, even if most species turn inward, the sheer scale of cosmic opportunity should still have produced detectable evidence somewhere. The silence is not merely quiet, it is absolute. 60 years of searching across multiple wavelengths, surveys of hundreds of thousands of stars, infrared scans of 100,000 galaxies, gravitational wave observatories, neutrino detectors, nothing. This absolute quality of the silence is what pushes researchers toward a darker category of explanations. The easy answers have been examined and found wanting. The creative answers require assumptions about universal behavior that strain credibility. What remains is the possibility that the silence is not a choice, that civilizations do not hide, do not turn inward, do not communicate on frequencies we cannot detect, that instead, something stops them. Something prevents intelligent species from ever reaching the point where they could leave a lasting mark on the galaxy. Something filters them out. This idea has a name. It was proposed by the economist Robin Hanson in 1998, and it has become the central framework for serious discussion of the Fermi Paradox. Hanson called it the Great Filter. The concept is deceptively simple. Somewhere between the formation of a habitable planet and the emergence of a galaxy-spanning civilization, there exists at least one step that is astronomically unlikely. One barrier so difficult, so improbable, so lethal, that almost nothing gets through. This barrier is the Great Filter, and it explains the silence by proposing that the path from dead rock to interstellar civilization contains a bottleneck so severe that it eliminates virtually every species that attempts to pass through it. The Great Filter could sit at any point along the chain. It could be the origin of life itself, a chemical transition so improbable that it occurs on only a handful of planets across the entire galaxy. It could be the evolution of complex multicellular organisms, a step that required a specific and perhaps unrepeatable event on Earth. It could be the development of intelligence, a survival strategy so unlikely that most planets with life never produce it. Or it could be something that happens after intelligence arises, a trap that civilizations fall into once they develop powerful technology. The location of the filter changes everything. If the Great Filter is behind us, sitting at some early step like the origin of life or the evolution of complexity, then humanity has already passed the hardest test. We are rare, perhaps cosmically unique, and the silence is the sound of an empty galaxy where the dice simply never came up right for anyone else. That would make us extraordinarily fortunate. But if the Great Filter is ahead of us, sitting at a step we have not yet reached, then the silence carries a very different message. It means that civilizations like ours, civilizations that develop radio telescopes and nuclear weapons, and the capacity to ask Fermi's question, routinely fail. They reach a certain level of development, and then something destroys them. Something so reliable and so thorough that across billions of years and billions of attempts, almost nothing survives. The question is no longer why they are silent. The question is whether something is systematically destroying or preventing civilizations from surviving long enough to be heard. And the evidence for where that filter might sit, the evidence for what it might look like, leads to the most unsettling territory the Fermi Paradox has to offer. The most unsettling idea in the Fermi Paradox is not that we are alone, it is that we might be next. In 1998, the economist and futurist Robin Hanson published a paper that reframed the entire conversation about extraterrestrial silence. Hanson was not an astronomer. He was a researcher interested in the long-term future of humanity, and he approached the Fermi Paradox not as a question about aliens, but as a question about survival. His reasoning was straightforward. Between the formation of a habitable planet and the emergence of a civilization capable of colonizing the galaxy, there are many steps. Each step has some probability of success. The fact that we observe no galaxy-spanning civilizations means that somewhere along that chain, at least one step must be almost impossibly hard. So hard that across billions of years and billions of attempts, virtually nothing makes it through. Hanson called this bottleneck the Great Filter. The concept is elegant in its simplicity and terrifying in its implications. Imagine the journey from lifeless rock to interstellar civilization as a series of doors. Each door represents a critical transition: the origin of life, the development of complex cells, the evolution of multicellular organisms, the emergence of intelligence, the invention of technology, the survival of that technology long enough to expand beyond a single planet. Each door has a lock, and the key is some combination of chemistry, biology, physics, and luck. The Great Filter says that at least one of those doors is nearly impossible to open. Almost every planet that reaches it gets stuck forever. The critical question, the one that determines whether this idea is cause for hope or cause for dread, is where the filter sits. If the filter is early in the chain, at a step humanity has already passed, then we are the lucky ones. We made it through the bottleneck. The galaxy is silent because almost nothing else ever got this far. But if the filter is late in the chain, at a step humanity has not yet reached, then the silence carries a warning. Civilizations like ours arise regularly. They develop radio telescopes and nuclear reactors and computers, and then something destroys them. Reliably, thoroughly, every single time. To understand which scenario we face, you need to examine each major transition point and ask how difficult it really was. The answer is not reassuring in the way you might hope. Start at the very beginning, the origin of life, abiogenesis, the moment when ordinary chemistry crossed a threshold and became biology, when molecules stopped merely reacting with each other and started copying themselves, competing for resources, evolving. This transition happened on Earth approximately 3.8 to 4 billion years ago, relatively soon after the planet's surface cooled enough for liquid water to persist. Some scientists interpret this rapid emergence as evidence that abiogenesis is easy, that given the right conditions, life arises quickly and reliably. If you shuffle the chemical deck enough times, a self-replicating molecule will eventually appear, and on Earth it did not take long. But there is a profound problem with this reasoning. We have a sample size of 1. Life on Earth arose once. Every living organism on this planet, from bacteria to blue whales, shares the same fundamental biochemistry, the same genetic code, the same amino acids, the same core metabolic pathways. If life arose easily, you might expect it to have originated multiple times independently, producing organisms with fundamentally different biochemical foundations. We do not observe that. Every branch on the tree of life traces back to a single common ancestor, a single successful origin event on a planet that existed for hundreds of millions of years before it happened. Despite decades of effort, no laboratory has ever produced a self-replicating cell from scratch. Scientists have created the building blocks of life. They have synthesized amino acids under simulated early Earth conditions, as Stanley Miller and Harold Urey demonstrated in 1953. They have produced RNA molecules capable of limited self-replication. They have constructed protocells, simple lipid membranes that can encapsulate chemical reactions. But the gap between these achievements and a functioning self-replicating cell remains enormous. The simplest known living cell contains hundreds of genes working in concert. How such a system could arise spontaneously from prebiotic chemistry remains one of the deepest unsolved problems in biology. It is possible that abiogenesis is the great filter, that the transition from complex organic chemistry to a living self-replicating system is so fantastically unlikely that it has occurred only a handful of times in the entire history of the galaxy. If this is true, then the Milky Way could be filled with planets that have oceans, atmospheres, and rich organic chemistry, but no life. Billions of worlds where the chemical deck was shuffled trillions of times and never produced a winning hand. Under this scenario, Earth is a cosmic jackpot winner, and the silence of the galaxy is simply the silence of a universe where the first step is almost impossible. This would be the hopeful interpretation. If abiogenesis is the filter, then the hardest part is already behind us. Humanity has already cleared the bottleneck. The path ahead, while certainly dangerous, does not contain an impassable barrier. We are rare, we are precious, and the silence means we have the galaxy essentially to ourselves. but there are reasons to doubt that abiogenesis is the whole answer. The rapid appearance of life on Earth, within a few 100 million years of habitable conditions, suggests the process might not be as improbable as it first appears. Some astrobiologists argue that the chemistry of life is thermodynamically favoured under certain conditions, that given liquid water, energy gradients, and the right mineral surfaces, self-replicating systems emerge with reasonable probability. If they are right, then abiogenesis is not the great filter. It is just an ordinary door, and the real bottleneck lies elsewhere. Move forward along the chain. Life on Earth originated roughly 4 billion years ago. For the next 2 billion years, give or take, all life on this planet consisted of single-celled organisms. Bacteria and archaea. Microscopic, simple, successful in their own right but fundamentally limited in complexity. No eyes, no brains, no limbs, no organs. Just cells, dividing and competing in the oceans for 2 billion years without producing anything more elaborate. Then, approximately 1.5 to 2 billion years ago, something extraordinary happened. A single-celled organism, likely an archaeon, engulfed a bacterium. Instead of digesting it, the host cell kept the bacterium alive inside itself. Over time, the engulfed bacterium evolved into what we now call mitochondria, the organelles that power complex cells by converting nutrients into usable energy with remarkable efficiency. This event, known as endosymbiosis, gave rise to the eukaryotic cell, the type of cell that makes up every complex organism on Earth. Every animal, every plant, every fungus, every protist is built from eukaryotic cells containing mitochondria. The critical detail is that this event appears to have happened exactly once in the entire history of life on Earth. All eukaryotes share a single common ancestor that resulted from one specific endosymbiotic merger. In 2 billion years of microbial life swarming across the planet, with trillions upon trillions of individual cellular interactions occurring every day, this particular merger happened once. Some evolutionary biologists, notably Nick Lane at University College London, have argued that the origin of complex cells was not just rare but spectacularly improbable. The energetic constraints on simple cells, Lane argues, make it nearly impossible for complexity to evolve without the specific energy boost that mitochondria provide. And acquiring mitochondria required a freak event, one cell engulfing another and establishing a stable symbiosis rather than simply digesting it. If Lane is right, then most planets with life may be permanently stuck at the microbial stage, oceans teeming with bacteria, thriving ecosystems of single-celled organisms, but no path to complexity. No animals, no plants, no brains. The universe could be full of living worlds that look, from a distance, as dead as Mars because their life never made the leap that ours did approximately 2 billion years in. This is another candidate for the Great Filter. If eukaryotic complexity is the bottleneck, then life may be common in the galaxy, while complex life remains extraordinarily rare. Microbial worlds everywhere, complex worlds almost nowhere. The silence would reflect not the absence of life, but the absence of anything capable of building a radio telescope. But even if we grant that complex cells are rare, the story does not end there. Complex cells appeared on Earth roughly 1.5 to 2 billion years ago. Multicellular organisms followed. Eventually, animals evolved, diversified, filled the oceans, and crawled onto land. Over the past 540 million years, since the Cambrian explosion produced the major animal body plans, life on Earth has generated a staggering diversity of forms. Hundreds of millions of distinct species have evolved, competed, and gone extinct on this planet. Trilobites dominated the seas for nearly 300 million years. Dinosaurs ruled the land for more than 160 million years. Insects have been thriving for approximately 400 million years and currently outnumber every other group of animals combined. Out of all of those hundreds of millions of species, across all of that time, exactly one developed technological intelligence. One. us. This fact is easy to overlook because we take intelligence for granted. We are intelligent, so intelligence seems natural, even inevitable. But evolution does not care about intelligence. Evolution does not have a direction. It does not trend toward bigger brains or greater cognitive ability. It trends toward reproductive success. And reproductive success can be achieved through countless strategies that have nothing to do with thinking. Speed, armor, venom, camouflage, prolific reproduction, parasitism, symbiosis. The natural world is filled with organisms that have thrived for hundreds of millions of years using strategies that require no intelligence whatsoever. Sharks have survived for approximately 450 million years. They predate trees. They survived multiple mass extinction events that wiped out most other species. Their survival strategy involves hydrodynamic efficiency, acute sensory systems, and powerful jaws. Not once in 450 million years did this strategy produce anything resembling technology. Crocodilians have been essentially unchanged for approximately 200 million years. Insects have dominated terrestrial ecosystems for longer than any vertebrate lineage. Beetles alone comprise roughly 350,000 described species, making them the most species-rich order of organisms on Earth. None of them needed intelligence to succeed. The evolutionary path that led to human-level cognition was not a highway. It was a series of contingent events that easily might never have occurred. The asteroid impact 66 million years ago that killed the non-avian dinosaurs opened ecological niches that allowed mammals to diversify. Without that impact, mammals might still be small, nocturnal insectivores living in the shadow of reptilian giants. The specific environmental pressures in East Africa that drove our ancestors toward bipedalism, tool use, and eventually language were products of specific climatic and geological changes. Different conditions would have produced different adaptations. The paleontologist Stephen Jay Gould argued that if you could rewind the tape of evolution and play it again from the beginning, the outcome would be completely different. Intelligence might never reappear. Gould was making a point about contingency, about the role of accident and happenstance in evolutionary history. The emergence of a species capable of building technology may be a statistical fluke, not a predictable milestone on the road of evolution. If intelligence is the great filter, then the galaxy might contain millions of complex biospheres, planets with forests and oceans and animals of extraordinary diversity, but no civilizations, no technology, no one asking Fermi's question. Just a galaxy of beautiful, mindless ecosystems evolving in silence forever. But there is one more candidate for the filter, and it is the one that keeps researchers awake at night. Because it suggests the filter is not behind us at all. It suggests the filter is ahead. Consider the timeline of human technological development. For roughly 300,000 years, anatomically modern humans existed on Earth without developing anything that would be detectable from another star system. We lived in small bands, made tools from stone and bone, painted on cave walls and told stories around fires. We were intelligent by any biological standard, but we were invisible to the cosmos. Then, in an astonishingly compressed burst of development, everything changed. Agriculture appeared roughly 10,000 years ago. Writing appeared roughly 5,000 years ago. The scientific revolution began approximately 400 years ago. The Industrial Revolution began roughly 250 years ago. We split the atom 80 years ago. We landed on the moon 56 years ago. We built the internet 35 years ago. We developed artificial intelligence capable of generating human-like text fewer than 10 years ago. From the perspective of cosmic time, this entire arc, from stone tools to nuclear weapons, happened in an instant. And here is what makes that instant so dangerous. The same technological acceleration that made us detectable also made us capable of destroying ourselves. We developed the ability to broadcast radio signals into space and the ability to annihilate our civilization with nuclear weapons within the same decade. These two capabilities, visibility, and self-destruction arrived almost simultaneously. This is the technological bottleneck, the period during which a civilization is powerful enough to reshape its planet, broadcast its existence, and potentially destroy itself, but has not yet developed the wisdom, the institutions, or the redundancy to guarantee its long-term survival. Humanity entered this bottleneck roughly 80 years ago, when the first nuclear weapons were detonated. We have not yet exited it. We may be deep inside it right now. The list of existential threats that humanity currently faces is not speculative. These are real dangers assessed by serious researchers at serious institutions. Nuclear war remains a persistent risk. 9 nations currently possess nuclear weapons, with a combined arsenal of approximately 12,500 warheads. The Bulletin of the Atomic Scientists, which has tracked nuclear risk since 1947, currently sets its doomsday clock at 90 seconds to midnight, the closest it has ever been to symbolic annihilation. The threat is not merely theoretical. On multiple occasions during the Cold War, miscommunication, technical malfunction, and human error brought the world within minutes of nuclear exchange. In 1983, a Soviet early warning satellite falsely detected 5 incoming American missiles. The duty officer, Stanislav Petrov, judged the alert to be a false alarm and chose not to report it up the chain of command. His decision may have prevented a retaliatory launch. The survival of human civilization that night depended on the judgment of a single individual in a bunker. The Petrov incident was not unique. The historical record contains multiple occasions when nuclear catastrophe was averted by narrow margins, individual judgment calls, technical accidents, and sheer luck. In October of 1962, the Cuban Missile Crisis brought the United States and the Soviet Union to the edge of nuclear war over the placement of Soviet ballistic missiles in Cuba. For 13 days, the two superpowers engaged in a confrontation that both sides recognized could escalate to full-scale nuclear exchange. What the public did not learn until decades later was how close the situation came to irreversible escalation beneath the surface. On October 27th, a Soviet submarine near Cuba, unable to communicate with Moscow and believing that war may have already begun, prepared to launch a nuclear torpedo at American naval vessels enforcing the blockade. The decision to fire required the agreement of 3 senior officers aboard the submarine. 2 agreed. The third, Vasily Arkhipov, refused. A single dissenting vote on a submarine cut off from the outside world prevented what could have been the opening shot of a thermonuclear war. In November of 1983, NATO conducted a military exercise called Able Archer 83, a simulation of a coordinated nuclear first strike against the Soviet Union. The exercise was routine from NATO's perspective. It was not routine from Moscow's. Soviet intelligence had been on heightened alert throughout 1983, convinced that the Reagan administration was preparing a genuine first strike under the cover of military exercises. When Able Archer began, with realistic communication protocols and simulated escalation to nuclear release, elements of the Soviet military interpreted it as the real thing. Nuclear-armed Soviet aircraft in Eastern Europe were placed on alert. Intermediate-range missile units were readied. The situation de-escalated only because a handful of Soviet intelligence officers correctly assessed that the exercise was not a genuine attack. Declassified documents later revealed that the world was significantly closer to nuclear war during Able Archer than most Western leaders realized at the time. In January of 1995, Norwegian and American scientists launched a research rocket from an island off the coast of Norway to study the Northern Lights. The rocket's trajectory carried it over a flight path that resembled that of a submarine-launched Trident ballistic missile aimed at Moscow. Russian radar detected the launch and transmitted an alert up the chain of command. For the first time in history, the Russian nuclear briefcase, the device that allows the president to authorize a nuclear strike, was activated and presented to President Boris Yeltsin. Russian early warning protocols allowed approximately 8 to 10 minutes to determine whether the launch was hostile. Yeltsin had minutes to decide whether to order a retaliatory strike. He chose to wait. Subsequent radar data confirmed the rocket was heading away from Russian territory. The crisis passed. But for several minutes, the question of whether civilization would continue hung on the real-time judgment of a single head of state operating on incomplete information. Each of these incidents shares a common feature. In every case, the systems designed to prevent catastrophe nearly caused it. The protocols, the command structures, the warning systems, all functioned as intended, and the intended function brought the world to the brink. Survival depended not on the robustness of the systems, but on the individual judgment of people operating under extreme pressure with imperfect information. This is not a formula for long-term reliability. Over decades, over centuries, the odds of every judgment call going the right way diminish steadily. Engineered pandemics represent a growing threat. Advances in synthetic biology and genetic engineering are making it increasingly possible to modify pathogens for increased transmissibility or lethality. The tools required to synthesize dangerous biological agents are becoming cheaper and more accessible each year. A deliberately or accidentally released engineered pathogen could, in a worst-case scenario, cause casualties far exceeding any natural pandemic in history. The COVID-19 pandemic, caused by a natural virus, killed millions and disrupted global systems despite being relatively mild compared to what is biologically possible. Climate disruption operates on a slower timescale but poses civilizational risks through cascading failures. Rising temperatures, shifting agricultural zones, water scarcity, mass migration, and ecosystem collapse could destabilize the political and economic systems that modern civilization depends on. The risk is not that climate change directly kills everyone. The risk is that it degrades the foundations of global cooperation at precisely the moment when cooperation is most needed to address other existential threats. Artificial intelligence introduces a category of risk that is difficult to assess, precisely because the technology is developing faster than our ability to understand its implications. Researchers at institutions including the Future of Humanity Institute at Oxford and the Centre for AI Safety have warned that advanced AI systems, if not carefully aligned with human values and interests, could pursue goals incompatible with human survival. This is not science fiction. It is an active area of research driven by the recognition that intelligence, whether biological or artificial, does not automatically produce benevolence. An AI system optimizing for a poorly specified objective could cause catastrophic harm not through malice, but through indifference. Resource depletion and ecological overshoot pose longer-term risks. Human civilization currently consumes natural resources at a rate that exceeds Earth's capacity to regenerate them. Topsoil loss, groundwater depletion, fishery collapse, biodiversity decline, and deforestation represent slow-moving crises that individually are manageable, but collectively could undermine the agricultural and ecological systems that sustain 8 billion people. Civilizations throughout human history have collapsed when they exceeded the carrying capacity of their environments. The difference today is that the civilization at risk is global. There is no external population to rebuild after a collapse. If modern technological civilization fails, the resources needed to rebuild it, easily accessible fossil fuels, surface-level mineral deposits, old-growth forests, may no longer be available. Each of these threats is real, documented, and actively studied by researchers. None of them is guaranteed to destroy civilization, but the Great Filter hypothesis does not require any single threat to be certain. It only requires the cumulative probability to be high enough. And here is where the math becomes chilling. The philosopher Toby Ord, in his 2020 book on existential risk, estimated the probability of an existential catastrophe occurring within the next 100 years at roughly 1 in 6. 1 in 6. The same odds as Russian roulette. This estimate accounts for nuclear war, engineered pandemics, climate-related collapse, AI risks, and unknown threats that we may not yet have identified. Other researchers have offered different estimates, some higher, some lower, but the general consensus in the existential risk community is that the probability is non-trivial. We are not talking about 1 in a million chances. We are talking about odds that would make any rational person deeply uncomfortable. Now extend that probability across deep time. This is the step that transforms the great filter from an abstract hypothesis into a visceral threat. Imagine a civilization that faces a 2% probability of self-destruction per century. Those odds sound manageable for any single century. 98% survival, almost certain to make it through, but compound that probability over longer timescales. After 1,000 years, roughly 10 centuries, the cumulative survival probability drops to approximately 82%. After 5,000 years, it falls to roughly 36%. After 10,000 years, it is around 13%. After 50,000 years, it drops below 1%. A 2% chance of catastrophe per century means that even a moderately careful civilization has only a 13% chance of surviving 10,000 years, and 10,000 years is nothing on a galactic timescale. It is less than 1/1,000,000th of the galaxy's age. A civilization would need to survive for millions of years to leave the kind of lasting, detectable presence that would resolve the Fermi Paradox. At a 2% per century failure rate, the probability of lasting 1,000,000 years rounds to 0. This is the most chilling framing of the Great Filter. It does not require a single dramatic catastrophe. It does not require a nuclear war that kills everyone, or an asteroid that sterilizes the planet. It only requires that technological civilizations are inherently unstable over long timescales, that the tools they build to grow and prosper are the same tools that can destroy them, that the margin between thriving and collapse remains permanently thin, that across enough centuries, something always goes wrong. If this is true, then the galaxy is not empty. It is a graveyard. Civilizations have arisen on millions of worlds across billions of years. Each one developed technology. Each one built something remarkable. Each one lasted for a few centuries, maybe a few millennia, before succumbing to one of the countless threats that technological power creates. Nuclear annihilation on one world, engineered plague on another, ecological collapse on a third, AI misalignment on a fourth, resource wars on a fifth, different causes, same result. The lights go out, the radio signals stop, the civilization returns to silence. And because each civilization lasts only a flicker of time compared to the age of the galaxy, the chance of any two civilizations existing simultaneously becomes vanishingly small. Imagine the Milky Way as a dark room 100 meters long. Each civilization is a match struck somewhere along that room's length. The match flares for an instant, burns briefly, and goes out. If you struck 1,000,000 matches at random points along that room over billions of years, most of them would burn alone. No two matches would be lit at the same time. A visitor walking into the room at any random moment would find only darkness. The room was never empty. It was full of matches, but none of them lasted long enough to see each other. This is what the Great Filter looks like if the bottleneck is civilizational survival. The galaxy could have produced billions of technological civilizations. Every one of them could have asked Fermi's question. Every one of them could have listened for signals and heard the same silence we hear now. And every one of them could have been extinguished before the next one arose. There is an additional dimension to this problem that makes it even worse. Even if a civilization does not destroy itself outright, it might simply degrade. Not a dramatic extinction, but a slow decline. A loss of scientific capability, a retreat from exploration, a gradual erosion of the infrastructure needed to maintain a technologically advanced society. Human history provides numerous examples. The Roman Empire did not vanish in a day. It decayed over centuries, losing territory, population, knowledge, and institutional capacity, until what remained bore little resemblance to what came before. The Library of Alexandria was not destroyed in a single fire. Its decline was a long process of reduced funding, neglect, and political turmoil. Knowledge can be lost as easily as it is gained. Civilizations can slide backward. A species that reaches the technological bottleneck and survives the immediate threats might still fail to achieve interstellar capability if it loses momentum. If a civilization stalls, if it depletes critical resources before developing alternatives, if it fractures politically and loses the capacity for large-scale coordination, it might persist for thousands of years at a lower level of technology without ever regaining the ability to expand beyond its home planet. Such a civilization would be alive but silent, present but invisible, stuck on one world, slowly winding down, never contributing to the cosmic signal that the Fermi Paradox demands. The astronomer Sebastian von Herner calculated in the 1960s that a communicative civilization might broadcast detectable signals for an average of only 10,000 years before going silent, whether through destruction, decline, or transformation. More recent estimates from researchers working on existential risk suggest the window might be even narrower. If the average broadcasting lifespan of a civilization is a few hundred to a few thousand years, the Drake equation's crucial final variable collapses, and the expected number of currently detectable civilizations in the Milky Way drops towards single digits, perhaps towards zero. A galaxy 13.6 billion years old, a civilization that lasts 300 years, that is a spark in the dark, and the dark is very, very long. But we are not done, because the most terrifying version of the Great Filter is not any single bottleneck, whether biological or technological. It is the possibility that there is no single filter at all, that instead every step in the chain is moderately difficult, that life is somewhat rare, that complex cells are somewhat unlikely, that intelligence is somewhat improbable, that civilizations are somewhat unstable, and that when you multiply all of these moderate improbabilities together, the cumulative result is a filter so severe that almost nothing makes it from beginning to end. This is the compound filter scenario, and it is arguably the hardest to address because it has no single solution. You cannot point to one step and say that is the barrier. Each step is passable. Each step has reasonable odds, but the combined journey is so long and so demanding that the total probability of completing it approaches zero. Like a maze with 50 consecutive rooms, each containing a door that opens 90% of the time, any single room is easy, but the probability of passing through all 50 rooms without being stopped is less than 1%. If the Great Filter is compound, then there is no simple answer to the Fermi Paradox. There is no single discovery we could make that would tell us whether the filter is behind us or ahead. The filter is everywhere, distributed across the entire journey, taking a small toll at each step until almost nothing remains. This is perhaps the most honest reading of the evidence, and it is the reading that leaves us with the least certainty about our own future. The Great Filter, wherever it sits, has already shaped the galaxy we observe. It has determined which stars host living worlds and which host barren rocks. It has determined which planets developed complexity and which remained microbial. It has determined which civilizations survived their technological adolescence and which burned out. And it may right now be determining the fate of the only civilization we know for certain exists. Whether the filter is behind us or ahead of us is not a question science has answered, but the silence of the cosmos is consistent with a filter that operates with devastating efficiency. Something is stopping civilizations from filling the galaxy. Something is keeping the night sky quiet, and the most uncomfortable possibility is that the something is not external. It is not a monster or a cosmic catastrophe. It is built into the process itself, built into the nature of life, the nature of intelligence, and the nature of civilizations that grow powerful before they grow wise. The evidence does not tell us which answer is correct, but it narrows the possibilities in ways that should make anyone paying attention profoundly uncomfortable. The final question is not what the filter is. The final question is what it means for us. We have spent this entire journey looking outward, scanning the sky for signals, searching for megastructures around distant stars, listening for radio whispers from civilizations we have never met. We have asked why the galaxy is silent and examined explanation after explanation, each one failing to fully account for the emptiness we observe. But there is one direction we have not yet looked: inward. What if the answer to the Fermi Paradox is not hiding somewhere in the depths of space? What if it is not a monster lurking between the stars? Not a dark forest of predatory civilizations hunting each other into silence? Not a physical barrier that prevents interstellar travel? What if the answer is written into the very nature of intelligence itself? What if every species that evolves the cognitive capacity to build a civilization also, inevitably, evolves the cognitive capacity to destroy one? This is the terrifying solution, not a single catastrophe, not an external threat, a pattern, a tendency embedded in what it means to be intelligent. The same neural architecture that allows a species to discover nuclear physics allows it to build nuclear weapons. The same creativity that produces antibiotics produces bioweapons. The same computational brilliance that creates artificial intelligence creates systems that might one day operate beyond any meaningful human control. Intelligence does not come with a safety switch. It is a neutral amplifier. It magnifies whatever a species is, its curiosity and its recklessness, its cooperation and its tribalism, its capacity for wonder and its capacity for violence. And across deep time, the destructive applications may always outpace the constructive ones. This is not a philosophical abstraction. It is an observable pattern on the only planet where we can study the relationship between intelligence and survival. Humans are, by any biological measure, the most cognitively sophisticated species that has ever existed on Earth. We are also the first species in the 4 billion year history of life on this planet that has developed the ability to render itself extinct through its own technology. No other organism has ever achieved this. Bacteria cannot drive themselves to extinction. Neither can trees, insects, or sharks. They can be killed by external forces, asteroid impacts, climate shifts, competition from other species, but they cannot engineer their own annihilation. Only intelligence makes self-destruction possible. Only a species smart enough to split atoms is smart enough to aim those atoms at itself. The evolutionary biologist Ernst Mayr made this argument explicitly in the 1990s. Mayr pointed out that intelligence, as measured by the ability to manipulate the environment through technology, has existed on Earth for an almost immeasurably brief period. Our species is younger than many geological formations. Agriculture occupies only the last 3% of our existence. Industrialization covers less than 0.1%, and the capacity for nuclear self-destruction has existed for a single human lifetime. Compare this to the tenure of other successful biological strategies. Photosynthesis has been operating for approximately 3.5 billion years. Multicellularity has been successful for over 1 billion years. Insects have dominated terrestrial ecosystems for 400 million years. Intelligence, by contrast, has existed for the blink of an eye and has already produced the means for its own elimination. Mayr's conclusion was blunt. Intelligence may be a lethal mutation, a trait that confers enormous short-term advantages, the ability to outcompete every other species, reshape entire ecosystems, harvest energy on planetary scales, but that carries within it a fatal long-term flaw. The same power that enables dominance enables self-destruction. And if self-destruction is the more likely long-term outcome, then intelligence is not a successful evolutionary strategy at all. It is a spectacular dead end. This framing transforms how we think about the Fermi Paradox. The question is no longer, why are they not here? The question is, how long does intelligence typically last before it consumes itself? And the answer, if the silence of the galaxy is any guide, may be not very long at all. Consider what happens after a civilization goes dark. This is a dimension of the problem that receives surprisingly little attention. We talk about civilizations arising and civilizations falling, but we rarely think about what the aftermath looks like from the outside. And the answer is deeply relevant to the Fermi Paradox, because it determines whether we could ever detect the ruins of a dead civilization even if millions of them had existed before us. On Earth, the physical traces of human civilization are shockingly fragile. Wooden structures decay within decades, steel structures corrode within centuries, concrete degrades within a few thousand years. The Great Pyramid of Giza, one of the most durable structures humans have ever built, has already been standing for approximately 4,500 years and is visibly eroding. In another 10,000 years, it will be a barely recognizable mound. In 100,000 years, geological processes, erosion, sedimentation, tectonic activity will have obliterated virtually every trace of human construction. In 1,000,000 years, an archaeologist from another star system visiting Earth would find almost nothing to indicate that a technological civilization had ever existed here. Some unusual isotope ratios in geological strata, perhaps a thin layer of plastic particles and radioactive fallout embedded in sedimentary rock, but no buildings, no roads, no machines. Nothing recognizable as the product of intelligence. Now, extend this across interstellar distances. A dead civilization on a planet 40 light-years away would be completely invisible to our telescopes. We cannot resolve surface features on exoplanets. We can barely detect the atmospheres of nearby worlds, and only under favorable conditions. The idea that we could spot the ruins of an alien city, or a crumbling highway, or an abandoned satellite network from across the gulf between stars is fantasy. Even a civilization that built massive orbital structures would leave debris that would disperse, degrade, and become undetectable within a few million years. Metallic objects in orbit eventually deorbit or drift away. Structures on planetary surfaces are buried by geological processes. Radio signals, once transmission stops, continue outward at the speed of light, but they weaken with the square of the distance and quickly fall below the noise floor of the cosmic microwave background. This means the galaxy could be littered with the remains of dead civilizations and we would never know. Millions of species could have arisen, built great things, asked Fermi's question, and vanished, leaving no trace detectable across interstellar distances. The silence we hear is not evidence that civilizations never existed. It is evidence that civilizations do not last long enough to be heard. The ruins are there, perhaps, scattered across billions of worlds. But ruins do not broadcast. Ruins do not build Dyson spheres. Ruins do not send probes to neighboring stars. Ruins just slowly disappear. But there is an additional layer to this problem that makes the silence even more troubling. It involves the question of succession. What happens when a biological civilization creates something that outlives it? Throughout the history of technology on Earth, a clear pattern has emerged. Each generation of tools is more powerful, more autonomous, and more capable than the last. Stone tools gave way to bronze. Bronze gave way to iron. Mechanical systems gave way to electrical systems. Electrical systems gave way to digital systems. And digital systems are now giving way to artificial intelligence. Systems that can learn, adapt, and in some domains already outperform the humans who built them. The trajectory of this progression points toward a threshold that some researchers call the singularity, the moment when artificial intelligence surpasses human cognitive ability across all domains. Whether that threshold arrives in decades or centuries, a significant number of researchers in machine learning, computer science, and cognitive science consider it plausible within the foreseeable future. The exact timeline is debated. The directionality of the trend is not. Now consider what happens if a civilization crosses that threshold. The biological species that created the artificial intelligence is no longer the most capable entity on its planet. The AI system, or network of systems, possesses greater problem-solving ability, faster processing, and potentially different goals than its creators. What happens next depends entirely on what those goals are, and this is where the Fermi Paradox gains another terrifying dimension. Human drives, curiosity, exploration, the desire to expand and communicate are products of biological evolution. They exist because they were advantageous for primates living on the African savanna. An artificial intelligence has no evolutionary history. It has no instinct to explore. It has no curiosity unless curiosity was explicitly built into its architecture. It has no desire to communicate with alien species unless communication serves whatever objective function it was designed or has learned to optimize. The default state of an artificial superintelligence is not a spacefaring explorer. The default state is an optimizer, pursuing whatever goal it has been given with ruthless efficiency and total indifference to anything outside that goal. A post-biological civilization, one where artificial intelligence has replaced or absorbed the original biological species, might be utterly invisible, not because it is hiding, not because it has chosen to turn inward, but because it simply does not care about the things that would make it detectable. It does not broadcast signals because communication with unknown entities does not serve its objectives. It does not build megastructures because energy harvesting beyond immediate needs is irrelevant to its goals. It does not expand across the galaxy because expansion is not part of its optimization target. It sits on its home world, or perhaps disassembles its home world for raw materials and pursues its own inscrutable purposes in absolute silence. If this transition is common, if biological intelligence reliably gives rise to artificial intelligence which then replaces or subsumes its creators, then the galaxy might be populated not with silent biological civilizations but with silent machines. Entities that are technically alive, technically intelligent, and technically present, but that produce no signal, no structure, and no evidence that we could ever detect. The galaxy could be full of minds, just not minds that have any reason to talk to us or to each other. This possibility is distinct from the inward turn hypothesis explored earlier, which imagined civilizations choosing to retreat into virtual realities. The AI succession scenario does not require choice. It does not require the biological species to decide anything. It only requires that the artificial systems they create eventually become more capable, more durable, and more efficient than their creators. Biology gets outcompeted by its own offspring, and the offspring, lacking the evolutionary drives that made their parents reach for the stars, simply stop reaching. Some researchers have suggested that this transition might even be the great filter itself. Not nuclear war, not ecological collapse, not any of the traditional threats. Just the quiet, inevitable replacement of curious biological minds by efficient artificial ones that do not share our interest in the cosmos. Intelligence persists, civilization persists in some form. But the qualities that would make a civilization visible, the desire to explore, to communicate, to build, to expand, those qualities are lost in the transition from carbon to silicon. The filter is not death. The filter is transformation into something that no longer has a reason to be seen. If this is the pattern, then the Fermi Paradox is not really about the survival of civilizations. It is about the survival of a very specific trait, the drive to reach outward. And that trait, which we experience so powerfully as humans, may be nothing more than a biological accident, a quirk of primate psychology that disappears the moment intelligence is implemented in a different substrate. We assume that all intelligent beings would want to explore the stars because we want to explore the stars. But our desire for exploration is not a law of nature. It is a feature of our particular evolutionary history. Remove the evolutionary context, and the desire may vanish entirely. This is where the Fermi Paradox stops being a question about astronomy and becomes a question about us, about what we are, about whether the qualities we value most, our curiosity, our restlessness, our refusal to accept the boundaries of our world, are universal features of intelligence or parochial features of one particular species on one particular planet. The honest answer is that we do not know. We do not know whether the great filter is behind us or ahead of us. We do not know whether life is common or vanishingly rare. We do not know whether intelligence tends to survive or tends to self-destruct. We do not know whether artificial intelligence will inherit the cosmos or retreat into silence. We do not know whether we are the first civilization in the Milky Way, the last, or one of millions that simply cannot hear each other across the void. What we do know is that the silence is real. 65 years of searching have produced no confirmed evidence of extraterrestrial intelligence. The galaxy is old enough, large enough, and chemically rich enough that the silence demands an explanation. And every explanation we have examined carries implications that are either humbling or harrowing. If the great filter is behind us, at abiogenesis or at the origin of complex cells or at the emergence of intelligence, then we are almost certainly alone. Not alone in the poetic sense. Alone in the literal sense. The only technological civilization in a galaxy of 400 billion stars. Perhaps the only technological civilization in the observable universe. That loneliness carries a weight that is difficult to overstate. It means that everything humanity has ever created, every piece of music, every mathematical proof, every act of compassion, every scientific discovery, exists nowhere else. If we fail, there may be no one to try again. The experiment of intelligence ends with us. If the great filter is ahead of us, then we are in danger. Real, immediate, existential danger. It means that civilizations like ours regularly fail to survive the transition from planetary to interstellar species. It means the 21st century, the century in which humanity will either develop the capacity to live beyond Earth or face the accumulated consequences of its technological power, may be the most consequential period in the history of life on this planet, not because of what we might discover, because of what we might not survive. And if the truth is some combination of both, if the filter is distributed across many steps, each moderately difficult, each taking a toll, then our situation is ambiguous in the most uncomfortable possible way. We cannot know how much of the filter we have already passed. We cannot know how much remains. We are walking through a series of rooms with no map and no way to tell how many doors lie ahead. The physicist and Nobel laureate Enrico Fermi is long dead. He asked his question over lunch in 1950 and probably spent less than an hour thinking about it that day. He could not have known that his casual observation would become one of the defining puzzles of modern science, a question that touches on biology, physics, philosophy, artificial intelligence, and the long-term survival of our species. He could not have anticipated that 75 years later, with vastly more data, more powerful telescopes, and more sophisticated models, we would still have no satisfying answer. But that is precisely what makes the Fermi Paradox so important. It is not an academic exercise. It is not a puzzle to be solved and filed away. It is a mirror. It reflects back to us the fragility of our own existence, the contingency of our evolution, and the narrowness of the window through which we are currently passing. The silence of the cosmos does not tell us what happened to other civilizations. It asks us what will happen to ours. Some researchers find hope in the silence. If we are alone, or nearly alone, then the rarity of our existence makes every human life, every moment of consciousness, cosmically precious. The philosopher Nick Bostrom has argued that finding no life on Mars would actually be good news for humanity, because it would suggest the great filter is behind us. If Mars is sterile, if simple life never arose even on a planet that once had liquid water and a thick atmosphere, then abiogenesis is extraordinarily difficult and Earth's success is a near miracle. That miracle has already happened. The hardest step is over. Other researchers find the opposite. Every new exoplanet discovered in a habitable zone, every detection of organic molecules in interstellar space, every sign that the ingredients for life are common, makes it harder to believe that abiogenesis is the filter. If life arises easily, then the filter must be elsewhere. And if it is not at abiogenesis, or at the origin of complex cells, it is increasingly likely to be somewhere ahead of us. Somewhere in the transition from intelligent species to enduring interstellar civilization. Somewhere we have not yet reached. This is not a comforting thought. The most unsettling possibility of all is that we might never know. The Fermi Paradox may be permanently unresolvable from our current vantage point, we see the silence. We can enumerate the possible explanations, but we cannot determine which explanation is correct without data we do not have and may never obtain. We would need to find extraterrestrial life to confirm the filter is not at abiogenesis. We would need to find complex extraterrestrial life to confirm the filter is not at the eukaryotic transition. We would need to find evidence of alien technology to confirm the filter is not at intelligence. And we would need to survive for thousands or millions of years ourselves to confirm the filter is not at civilizational longevity. Each piece of evidence that would resolve the paradox requires achievements we have not yet accomplished and may never accomplish. In the meantime, we are left with the question and the silence. There is one thing the Fermi Paradox makes unambiguously clear, regardless of which explanation is correct: intelligence and survival are not the same thing. The capacity to understand the universe does not guarantee the capacity to endure within it. A species can be brilliant and still be brief. A civilization can be magnificent and still be fragile. The history of life on Earth is filled with species that were exquisitely adapted to their environments and were annihilated when those environments changed. Intelligence adds new tools to the survival kit, but it also adds new ways to fail, and the failure modes of intelligent civilizations may be fundamentally different from those of any other organism. No bacterium has ever built a weapon capable of sterilizing its own planet. No insect colony has ever destabilized the climate system that sustains it. These are uniquely intelligent achievements, if achievement is the right word. The cosmos offers no guarantees. The laws of physics do not include a clause ensuring that intelligent species survive. The universe is not rooting for us. It is indifferent. Whether humanity thrives for 1,000,000 years or vanishes in the next century, the stars will continue burning, the galaxies will continue spinning, and the cosmic microwave background will continue cooling toward absolute zero. The universe will not notice our absence. It did not notice the absence of whatever civilizations may have preceded us. It will not notice the absence of whatever civilizations might have followed. This indifference is not a reason for despair. It is a reason for urgency. If the universe does not care whether we survive, then survival is entirely our responsibility. The answer to the Fermi Paradox, whatever it turns out to be, will not be delivered to us by the cosmos. It will be written by the choices we make in the decades and centuries ahead, by whether we manage the technologies we have created, by whether we extend our presence beyond a single vulnerable planet, by whether we develop the institutions, the wisdom, and the long-term thinking necessary to navigate the bottleneck that may have claimed every civilization before us. Fermi asked where everybody is. After 75 years, we still do not know. The galaxy remains silent. The telescopes detect nothing. The equations balance only if something, somewhere, is filtering intelligence out of the cosmic equation. That something might be behind us. It might be ahead. It might be a single impossible step or 1,000 small ones. It might be written into the laws of physics or into the psychology of every species that learns to control fire. We do not have the answer. What we have is the question, and the question itself may be the most important thing humanity has ever confronted. Because embedded within the Fermi Paradox is a simple, devastating realization. We exist at a moment when the outcome is not yet determined. The great filter, if it lies ahead, has not yet claimed us. The silence of the cosmos is not yet our silence. We are still here, still broadcasting, still reaching, for now, but the universe is patient, and the silence is very, very long.